The lack of materials and live tissues is one important challenge for vet training and biology education. Compared to the 2D screen-based visualization of 3D anatomy models, mixed reality scientific visualization tools have shown more advantages in terms of 3D structure understanding and immersive learning. Virtual reality collaborative visualization tools allow for the best immersion, which gives the remote user a strong sense of presence in remote collaboration and tele-teaching use cases. However, motion sickness, safety considerations, and fatigue issues caused by long-time VR headset wearing have limited the usage of VR headsets. Moreover, the instability of technology-mediated communication for remote collaboration have been proved to cause frustration. For co-located educational tasks, separating users from their physical surroundings and collaborators can also reduce their sense of co-presence by blocking their natural communication. Therefore, handheld AR devices such as smartphones and tablets have been increasingly popular for immersive learning. As a daily use devices, this solution seems to be cheap and ideal enough for many application scenarios. However, handheld AR still shows limitations in certain application scenarios, where the users must continue the task at hand. Compared to VR headsets and handheld AR headsets such as Microsoft HoloLens provide 6 degrees of freedom gesture manipulation and stereoscopic 3D content observation. The hands-free AR visualization modality also allows the user to focus on their task at hand. But the high prices of these advanced AR headsets are still impeding the large-scale application in many schools and universities. Based on the above pros and cons of different mixed reality solutions, hybrid solutions have been proposed to allow for the remote collaboration between VR and AR headsets, which combine the advantages of both technologies. But such hybrid solutions still left the co-located natural communication issues unsolved. Students cannot naturally communicate with each other when they all wear the VR headsets. Also, such solution still requires high cost for large-scale applications. Asymmetric mixed reality solutions also have been proposed to support tele-teaching using a VR headset and multiple light field displays, which allowed one remote teacher to present 3D teaching materials within a virtual classroom, while multiple co-located students may observe the shared teaching contents using light field displays. Looking glass display is a type of light field display, which enables 3D experiences with seamless motion parallax and binocular parallax without the requirements of wearing a headset or glasses. Additionally, prior work has adapted looking glass display to support multi-user observations. Therefore, compared to equipping each student with a VR or AR headset, such light field displays may lead to averagely lower equipment cost. In most collaborative immersive learning contexts, the teacher and students normally play different roles. The teacher needs to select, illustrate, manipulate, and share the virtual teaching materials to the students with vocal explanations according to the students' responses, while the students need to observe and discuss the shared virtual material with classmates, and may also ask the teachers relevant questions. According to their different roles, the proposed metal system consists of the teacher client equipped with the Microsoft HoloLens 2 and multiple student clients equipped with the looking glass display. In metal system, one teacher wears an AR headset to manipulate and share different 3D contents to multiple groups of students. And each group of students can observe the shared 3D contents from different perspectives using one light field display. Each light field display is adapted to be capable for different 3D content display in multiple viewing zones, which allows the teacher to share multiple 3D contents with the same group of students. Therefore, one-to-M network connections can be established for online 3D content sharing among the teacher and students. From the perspective of the teacher client, the teacher is allowed to see what student can see. For example, the highlighted light field displays. Following the superimposed instruction, the teacher can drag an arbitrary anatomy and drop it to any recognized light field display for content sharing. Then, the real-time contents displayed in both viewing zones are also superimposed over each light field display, so that the teacher can manipulate the virtual content according to what these students can see. To facilitate teaching content manipulation, the teacher is also allowed to see what students cannot see. On the shared play area, the teacher can rotate and scale the shared contents in corresponding sub-area. These 3D model manipulations are real-time synchronized to corresponding student clients and viewing zones. Each student group is treated as one student client, and they can observe the shared 3D content using one light field display. In the same student group, the student standing on the left can observe the stereo 3D content of the left viewing zone with motion parallax. And the student standing on the right can observe the content from the right viewing zone. Therefore, even in the same student group, each student may see different 3D contents from different viewing zones. Of course, with motion parallax. So, demo time. In the future, we hope to allow the teacher to assign personalized contents targeted at different students. To satisfy this potential requirement, each light field display should be adapted to recognize students' identities and provide dynamic viewing zones that follow their head movement. At the same time, the teacher client should also be able to drop in virtual 3D models to any recognized students for targeted content sharing. Thank you for watching.